So today we're going to look at Maclaurin series.
It's possible to approximate a function by using a series in ascending powers of x. The Maclaurin series is a specific example of such a series. Just to give you a bit of the background, Colin Maclaurin lived in the first half of the 1700s. He was born in 1698 and died in 1746. So he was a contemporary with Leonhard Euler and Sir Isaac Newton. But he was a child prodigy, and by the age of 11, he was starting at university. And 3 years later, he graduated and he defended a thesis on the power of gravity. That might not sound so impressive, but bear in mind, we are talking about 1710. What was particularly impressive, though, was that he became a professor of maths at Aberdeen University when he was 19 years old. So apparently that's the youngest person ever to have been a professor. At least he held that record until quite recently, 2008. But anyway, that's Colin Maclaurin, the Scotsman, who we are indebted to for this series. But what is this series about? Well, you might remember during the first year of the further maths course that we used the Maclaurin series for some standard expansions that we have listed here. And there they are. And we went on and combined functions to form a compound function. But what if you are asked to find the Maclaurin series expansion for a function that isn't one of these or a combination of them? Well, in order to do that, you need to use the series formula. And in the second year of the course, that is what will be expected of you. And there it is, the Maclaurin series formula. And we can use this to derive the expansion for different functions. Just point out at this stage that for the function ln of 1 plus x, there's a limited range of values of x for which it's possible to do this expansion. And later on, we'll come back and see why that is. Now, before I do an example of and apply this formula to a function and form the expansion, I just want to go over with you why it works as it does and why it's this particular function that we're going to be using. So the curve, you'll notice that it's an exponential. It's actually y equals e to the x. And we want to approximate that. We're going to start off by just approximating it with a linear function, so a straight line graph. So in order to do that, we want to, first of all, choose a point on the curve. It's going to go through one point on the curve. And we also want to know the function that has the same gradient as that point. And what's special about the Maclaurin series is that Maclaurin used the y-intercept as his point. So for y equals e to the x, what we want to know is what is that point on the y-axis? Of course, x equals 0, and so e to the 0 equals 1. Then we also need to know the gradient at that point. So the gradient, well, if we differentiate e to the x, it stays as e to the x. No matter how often we differentiate it, it stays as e to the x. And so again, our x value is 0. So at that point on the y-axis, when x equals 0, our gradient is 1. So what's the linear function which has a gradient of 1 and also a y-intercept of 1? But for the sake of our series expansion, I'm going to rearrange it slightly and put it like that. So it is an approximation to our function. But at this stage, it's not a great approximation, is it? Or at least for a very narrow band of x values. So we're going to see if we can make an improvement on that. And what we're going to do, we're going to say, suppose we've got a curve which not only has the same point, as that point on our function not only has the same gradient, but also the second derivative as that. So what we're looking for then is the quadratic. Because a quadratic has the advantage over the linear that it has a second derivative. So for our function, y-intercept hasn't changed, nor has the gradient at that point. And as I said, however often we differentiate, we'll still have the second and third differentials and so on. We'll still have that same value as 1. So what quadratic function can we approximate to y equals e to the x, which has got those qualities? Well, it's also true for that quadratic. You can see if we substitute in x equals 0, the function has a value of 1. If we differentiate it, we lose the first term, and the second term will change to a 1. And then the x squared term multiply by 2, so that will become just x. So that when we find the second derivative, this term being x will then differentiate just to 1, which is what we're after for our second derivative. So let's have a look at that function. And there we are, the red quadratic. It's a lot closer to the green curve, isn't it, compared to that straight line. Let's lose the red straight line. And especially for positive x values, that's looking not a bad fit for our function. However, we can do better. We can improve it by taking further powers of x and further differentials. So our quadratic matches up to the second derivative. To get a third derivative, then we're going to have to work with a cubic. So for our y-intercept, first, second, and now third differentials, then our value for our function is always going to be 1. And there's the cubic for which that is also true. So just take a moment, have a look at that last term in the sequence, our cubic term. It's 1/6 x cubed. Why does it have to be 1/6? It's 1/6 because when we differentiate it, well, it will be multiplied by the power 3 first of all, won't it? Once that's been differentiated, it will be 3/6 x squared, or half x squared. And then the next power down is the 2, so it will then be multiplied by 2. So half x squared multiplied by 2, reduce the power by 1, just leaves us with an x. Then you can think the x is x power 1, so when that's differentiated, we just multiply by 1, and that last term becomes a 1, which is what we need for our third differential to be 1. But what it does highlight is that 6 is made up of the factors of 1, 2, and 3. So instead of 6, we could have written 3 factorial. And the same is true for the 2 in the x squared term. We could have written 2 factorial, 2 times 1. Well, let's have a look at what our this cubic is going to look like. And compared to the quadratic, that's an even better approximation, isn't it? It's even better for positive values of x, and definitely better for the negative values of x, just up past -1. So here's our cubic on its own. So what we're doing is we're saying our function is approximately equal to, first of all, f of 0, so that is the y-intercept, plus the gradient when x is 0 times x. So that gives us the linear function y equals mx plus c. So it goes through the point on the y-axis and with the same gradient. There it is. We said we can improve it by turning that into a quadratic, and we found the second derivative for x equals 0, and so by using x squared over 2 factorial, this will give us a second derivative, the same as our function when x is 0, and so on. Same with the cubic. By finding the f triple dash of 0 gives us the same third derivative when x is 0. And here's the function, the formula that I showed you at the start. This is the Maclaurin series formula. And we're going to use that in a minute to have a look at an example. But there's a couple of things that I've assumed so far that we need to be aware of, and it's worked fine for y equals e to the x. But what we're doing here is we're saying that each term can be differentiated. So our function at the start can be differentiated. And then our differential can be differentiated again to find the second derivative. We can find the third derivative, and so on. Each term can be differentiated. But not only that, we're saying that each of those terms, you can sub in x equals 0. You can find the gradient for x equals 0. You can find the second derivative for x equals 0, and so on. So this is a quality of a function for when you want to find the Maclaurin series expansion. And it's a key thing to be aware of when, if you're asked a question, explain why you can find the Maclaurin series expansion, or why you can't find a Maclaurin series expansion for the given function. It's worth just remembering now about the standard expansion for ln of 1 plus x, and that limited range of values that we're allowed to use it for. Part of that is to do with this, and if we use certain values of x, then we can't find the ln of 1 plus x, and that is why it's 1 plus x rather than just the ln of x that we have an expansion for.
Let's have a look at this example together. So we're being asked to derive the Maclaurin series expansion, and so that when it says derive, it's telling us use the formula. So I've written that out here. Even if we weren't told that, looking at the function, it's arc sine or inverse sine of x, and so that's not a standard one, so that's probably one that you're going to have to derive anyway. So the other information we're told is how far to take the expansion. So that's how far I've written out the formula for it. So what we need to do now is, in turn, we need to find the f of 0, the first differential, and then sub in x equals 0, second differential, sub in x equals 0, and the same for the third. So we'll take them one at a time. So first of all, f of x, we know that the f of x is in arc sine x. So f of 0, we can go straight there, equals arc sine of 0. So this is the inverse function, and so what it's asking us is for what angle do we get a sine ratio of 0. And so sine of 0 is 0. So our answer there is 0. Okay, how about then, first of all, the differential. Sorry, the differential of x. To differentiate arc sine x, well, that is a standard differential which you can find in the formula booklet. You might be asked to prove it, but we will just quote it for now. And that equals 1 over square root of 1 minus x squared. And so to substitute in 0 into the formula, it's going to be 1 minus 0 is just 1, so it's 1 over the square root of 1. So far so good. How about the second differential? So first of all, we'll find the second differential for x and then sub in 0. So if we write this as 1 minus x squared to the power of minus a half, we can use the chain rule more easily on it. So we're finding the differential of and so we can multiply by the power, multiplied by the differential of the bracket, so times minus 2x. Then the bracket stays the same, and we reduce the power by 1. So the minus half times the minus 2 cancel out to make 1. So we've got x, and that's to the minus power, negative power, so it's below the fraction bar. So we've worked out f dash of x. Now how about f dash, sorry, second derivative of 0. So we're going to substitute 0 in here, so we get a denominator will be 1, so that's fine, it's a finite value, but the numerator will be 0, so the second derivative of 0 is 0. So the values we're after here are 0, 1 and 0. So we just need to find out one more. We want the third derivative of x first of all, then we'll find the third derivative of 0. And so we're going to differentiate this. Differentiating all that. So more than one way we could do this. We can treat it as a quotient and differentiate it using the quotient rule, and so the rule, state the rule, d by dx of u over v equals v times the differential of u minus u times differential of v over v squared. So in our function, u is the numerator, which is just x, so the differential of that is 1, the denominator is, and so the differential equals, so times by the power times by the differential of the bracket times by the bracket, and reduce the power by 1. So the 2's cancel out, gives us minus 3x. So you can now sub that into our formula. So v times the differential of u is just 1 minus x squared to the 3 over 2. Then subtract u times the differential of v, so x times this. So that gives us an x squared. So it's going to be minus 3x squared. Changes that to a plus 1 minus x squared to the power of a half. And then underneath we've got v squared. It's the bracket to the 3 over 2, so if we square it, put to the power of 3. See, we can factorise out a factor of 1 minus x squared to the power of half. That's common to both terms on top and on the bottom. So if we take out 1 minus x squared to the power of a half, what we've got left inside, so that's to the 3 over 2, that's 1 and a half, take out the power of a half, leaves us just with a to the power of 1, so it's just 1 minus x squared. We've taken out this to the power of half, which just leaves plus 3x squared, and then on the denominator, if we take out a factor of 1 minus x squared to the half, leaves us with 3 take away half is 2.5, so power of 5 over 2. They cancel, and on the top that leaves 1 plus 2x squared all over our bracket to the 5 over 2 or 2.5. So we've got our function. We now want to substitute value of 0 into it, so it's the third differential of 0. So we substitute 0 into the numerator, gives us 1, into the denominator, still gives us 1. So it's just 1. So we're almost there. We've worked out all our coefficients. So these ones in green are what we're interested in. So the first term in our formula is the f of 0, which is 0, so we can ignore that. Then our coefficient of x is going to be 1. So f of x equals, that's the coefficient of x, so 1 lot of x. Then second derivative of 0 is 0, so our x squared term will disappear. Our x cubed term, our third derivative is 1, so it's going to be 1 times x cubed over 3 factorial. So it's just plus x cubed over 3 factorial, which is 6. And there we have it, our final answer.